Hello everyone, welcome to the episode 3 of the Learn with Z. So let me recap what we have learned in the first and second episode. First, we talk about electromagnetic wave, why we call it wave. Because when the signal propagate, the E field and the M field will react to each other, so it will oscillate. In the second episode, we talk about what's dB and what's the real life meaning of dB. We also mentioned the example of humans' hertz range is 20 to 220K, right? So one thing I want to add is that for elephant and mouse, in terms of the range of frequency of their hearing, who is bigger? Think about this for a little bit, right? Elephant, they are bigger. Mouse, they're very small. If you think this mouse and elephant as a receiver antenna, whose size will be bigger? Elephant, right? So we all know there is a relationship between wavelengths and the frequency, which is when the wavelength goes, well, there's another one, right? So when the wavelengths go up, the antenna size will tend to go up. They have a, they have a, you know, they have a positive relation. So that means when this go up, this will go down, right? The frequency will go down. That means elephant is big, its size will be big. So the wavelengths will be longer. So the frequency will be very small, right? For mouse is the opposite. Size is small, the length will be small. The wavelengths will be short. Frequency will be up. And in the real life, elephant have an upper limit of this, and they usually communicate with each other in a very small sound. We talk about infrasound, right? For mouse, they have something around 65 to 80 kHz. So that's that. I hope you can learn a little bit from this. That can explain the relationship between this. Right? This is very important. Okay. Today we're going to talk about the free space path loss, FSPL. There are so many terminology in the field of wireless communication that blocking me from learning further. But if you use Elon Musk's first principle, analyze everything from ground up, you will see actually it's not that difficult. So when we talk about free space path law, what are we talking about is imagine we have a transmitter antenna. Around this antenna, what will be the power loss in any point in the air? Say we have a antenna here. What is the path loss in this, right? Okay, think. What is the factor in this process? I would say it should be two things. First things, in terms of the substance you use to propagate, right? There will be a lot of friction between the signal and the air. Also, there's a lot of things in the air. It could be water and anything, right? But just think about that. The longer the distance, the more friction we'll have. So the more power loss we'll have. That means the first element will be the distance. If you talk to somebody in 5 meters range, you likely to have a higher volume than talking to somebody in 20 meters range. What's the second one? So when we talk about magnetic wave, there are actually two things. If we know two things, we tend to know everything. One is the P, power, and the other is frequency or lambda wavelengths. For electromagnetic wave, it looked like this, right? We will have another episode talk about this alone. So what is a wavelength? Wavelength is the distance between two peaks, or the distance between, a complete sine pseudo wave. We call this wavelength. How to differentiate between signal 1 and signal 2 is the shape of this image, right? The other one could be like this, right? But everything we know, because they are all sine pseudo wave and they will have the same factor. One is the power, the other is the wavelength or the frequency, right? So we know the wavelength is a very abstract concept, but if we apply this to real life in the 3 dimension, well, in 3 way, first I would talk about in the light. Shorter wavelengths tend to be blue. Longer tend to be red. Just remember this. I don't know why yet, but I will find out and I will teach you in the later episode. For the sound, shorter wavelengths, longer wavelengths. This will have high pitch. Like do, re, mi, fa, sol have a higher pitch. Because shorter wavelength means higher frequency. A higher frequency means higher pitch. In the electromagnetic wave, the signal, there is a relationship that we just talked about here, right? Which means the wavelengths usually have a positive relationship with L, the size. Think about Wi-Fi router. It's very small, kind of like this, have a 2.4 gigahertz frequency. And when we talk about the conventional 900 mHz, it's like a big box, right? So that means bigger the size, bigger the wavelength, smaller the frequency. Okay. Now it seems everything is clear now, right? Everything is clear. One more thing I want to mention is if you want to learn something well, try to explain the things to other people, then you can learn well. It's Feynman's way of learning. So here we know the distance and frequency or lambda or power matters, right? So what's the next step? So if we want to know a point in the air that have a distance of r with the transmitters, the first thing we need to know is a range of this r. Because it's kind of like this. It's kind of like a sphere, right? Of course, it's 3D. I'm looking at it at a 2D. So it will have an area of this r, which is 4 pi. This is an area, right? Two dimension. It's a area. So then we have this term called power density, which is the power divided by this area. That we know at the distance, the power density will be like this, right? But for the receiving antenna, it will have an effective aperture. We call it AR. And this AR, we have something called PR, the power of receiving, right? It will depend on the power density at those point and the aperture, effective aperture of that point. So what do we get is right, put it here, right? And we also define that AR equal G is a gain. How to visualize gain is that, think about something like this. If a sound from here to here, it will be bigger, right? So it has a positive. If sound is kind of like this, it will have a negative gain. So in this process, what we know is that PR will equal PT times gain times lambda square times, right? So we know PR and PT. What's the next step? We want to know the pass loss, right? So the pass loss, we tend to use the power at the transmitters minus the power at the receiver. We tend to use this. But in the wireless communication, people, they are so fancy, and actually it's more easier, to be honest. So what do we use? We use PT divide by PR. So later on, what we get? We get 20 log 10 R plus 20 log 10 F, because lambda, this can convert to, right? And we minus 147.55 dB. This equation is from Wikipedia, but you just look at this, you will know what will define a pass loss. It will always relate it to the distance and the frequency. The frequency will decide the wavelength. The wavelength, well, I would say the size will decide the wavelength. So that just connect all the dots together. Thanks for watching, and that's everything. Thank you so much.